What's up, Mike?
Hey, Paul. How are you?
I am so excited for this episode. This has been a long time in the making, and I was just telling our guests before we hit record that I had the idea for this episode when I was preparing some training materials for new employees who don't have as much exposure in the industry.
Okay.
And it's always, with my whole Thank a Machinist thing that I've been doing for years now, it blows me away just the incredible difference on the massive end and the tiny end of what machine shops do, right?
Yeah, yeah.
They're not just all making the same types of parts. You have parts that are super microscopic and you have parts that are, absolutely massive that take cranes and semi trucks to move around. And I thought it would just be fun to have a conversation about the difference, the contrast between the two wide ends of the machining spectrum.
We
You're in the
gosh.
middle, right?
Yeah, I think we're probably in that middle that covers 90% of the world, right? But
Yeah.
What's so interesting to me on both ends of the scale is like it took a while after I bought Hill for me to realize like we're not very good at small stuff.
Oh,
Like,
yeah.
if it's under 3/4 to a half inch like stock, we've gotten to where now we just no bid it because we are not good at that, and then of course we don't have the equipment for the really, really big stuff. But yeah, it's certainly a different part of the market, really, it seems like.
Yeah, it's part of the whole niche, right? You
Yeah.
gotta the best shops niche down and get really good at certain things. And I think our guests today certainly demonstrate that that's a good way to go because they are very specialized in their own niches on the far ends of the spectrum. So
Yeah, and just one note on that too, remember when you and I were in San Antonio and we toured that one shop, I can't remember the name of it.
yeah,
The glitter sized parts that they had. Remember that? I mean, they just
Yes.
like a whole handful, there's thousands of parts in your hand.
yeah, they had some of those nano Swiss machines.
Yeah,
I
that
can't
was
remember.
wild.
But that's more the end of
That's
the scale
impressive.
that Josh Hacko, who is with us, works in. And then we also have Jerry, who represents the other end. So let's introduce our guests here and hear a little bit about their backgrounds, a little bit about what their companies specialize in, and the size of parts they make. Josh, let's start with you.
Yeah, thank you very much for having me on. My name's Josh Hacko, and I'm the technical director of two sister companies. One is called Nicholas Hacko Watchmaker, and the other is NH Micro. And as you guys really, I think, touched on, we make really small parts, like super small parts, really complex parts, and very, very precise parts. So usually like those three spheres impinge on one another, and you get something in the middle, which is small, complex, and precise. And generally, that's like a watchmaking part. And so for the last 4 generations, my family has been repairing and restoring watches. And in the last maybe 10 to 15 years, we took the leap to start manufacturing watches, creating our own brand and manufacturing basically from raw materials to after sales service. So like that whole loop of being, I don't know, now that I'm more in the engineering world, I'd call it like an OEM. But our volumes are so small and it's still very like artisanal. So that's what we do. And we use a lot of very specialized machinery to manufacture the watch parts that also gives us a fairly significant maybe scope into manufacturing small parts for other industries. So the same machines that make watch parts end up making parts that go into space and into implants and into nuclear reactors and all sorts of other places. So thanks for having me on the show so I can talk about how small my world is. Yeah.
Love it. And Jerry, introduce yourself and your company and welcome to the show.
Yeah, thank you very much. I appreciate it. Jerry Kablak here, working at Baker Industries. Been here about a little over a decade now. We specialize in large machining, so fabrication, machining, inspection, primarily tooling, and shipboard components, hardware for different applications where it's aerospace, flight hardware, or even going into like the energy area. So
nuclear plants handling that material in that kind of range, as well as oil and gas and whatnot.
That's cool that you mentioned nuclear. So did Josh. So
Yeah.
obviously nuclear plants need tiny parts and need huge parts, which is super fun.
Absolutely.
So what is the
Absolutely.
scale of the parts that you make? Like, what is your biggest machine travels? How much do your parts weigh on the big end?
Yeah, so we have between, in the height, they're roughly 36, 38 CNC machines here. Our smallest machine will still hold a part roughly 36 to 40 inches in the X direction. But they can, obviously machine parts, I would say the smallest we would go down to is like something that would fit in your hand.
It's more like what Mike makes.
4 or 5, 4 or 5, 6 inches. That's about as small as we're going to go. But then we go up to like 50 feet.
Golly.
So our biggest machine has like an X travel about 46 feet. But we've actually had parts on that machine that were over 52 to 54 feet. I think we actually have room in the facility to machine something close to 70 feet, 75 feet.
Wow.
So that would be the biggest stuff that we're kind of looking at. And again, you get into big weldment structures and things like that. That's And believe it or not, there are some industries that are still look at us and say, "Hey, you're just not quite big enough." Like, there's always something. There's always something that could even be bigger and more. And I know that's the case. But you look at the for like a job shop that we kind of cut our teeth into. Baker's been around since the early '90s, and one of the first in the Midwest to kind of really adapt to 5-axis machining. So that kind of area, the niche market that we have has been pretty solid for us over the years.
Where are you located, Jerry?
Just north of Detroit, in Michigan.
And then Josh, you've got like a Northern Canadian accent or something. Is that right?
Gonna get me in trouble. I'm from Australia, in Sydney, Australia. Yep.
In the Sydney area, is that right?
That's right, in Sydney area. Yep.
Okay, very cool. So, Josh, tell us about. A couple questions for you, I guess. Tell us about the size of your parts, the actual size, and you can talk in millimeters because I'm sure that's what you talk in. But I'm guessing the fact that you have the two business sides, you have the watchmaking side, which you described, it's very cool, that many generations, and then more maybe the contract manufacturing side. Was that side of it started to use excess capacity from the machines that made watch parts? Because that is so common that shops, or companies they'll have a product and then they have lots of free time on their machines. They're like, well, let's just start some job shop work. And is that how yours started?
Yeah, that's basically exactly how we started. We had quite a lot of capacity because we were still learning how to develop a product, and we're going through like iterations where we needed quick turnaround, so we needed our own in-house machining capability. But all the time after you iterate on something is just idle time. So we didn't really necessarily go looking for job shop work, but inevitably once you have that capability, people start knocking on your door. And the first ever RFQ we got was for contact of a friend, of a colleague, of another friend who was in the F1 industry. And I said, we've got these tiny little gears that are supposed to go on the turbo vane housing to adjust the angles of the vanes on the inlet side. Can you make them? And I said, yeah, no problem. And I didn't even know what like a purchase order was or a quote was, or like that whole like business side just didn't even exist for me. So I sent an email back saying it's like, it'll be in the range between $100 and $200 per part. And that was for that type of part, just like insanely cheap. And they got looked over very quickly. But that feedback came through a few weeks later, and I said, interesting. There might be a market in this. And about, it's been now 6 or 7 years. So 7 years later, NH Micro, the contract manufacturing sites, around 75 or 80% of our revenue. So it's now dwarfed the watchmaking side. So we still do the watchmaking as a primary business, but it's so many facets to it. But what we think the most value that is brought by the watchmaking is that the guys who are working on the machines have an outlet for creativity. They have an outlet for something that can pour their passion into and see a physical product. A lot of the parts we make for other industries, they're incredible parts, but you can't show them to anyone, and that you don't really know what the final application is. You don't know where they go and how they interface with other components. Whereas the watch is something that's so tangible. So you end up learning a lot on your watch or your product, and then you move to something like contract manufacturing, and your skill set is just like applied properly on other people's work.
Super cool. Well, I found out about you because of LinkedIn, and when you post the pictures of the tiny parts you make, as we were talking about before, like on the tip of your finger where you can see your fingerprint up close, people love those. You get a ton of traction. And so that's how you got into my feed, and I started following you and connected, and here you are. But yeah, so tell us a little bit about the tiniest parts you've made.
Yeah, it's so funny how Jerry said like the small parts are like 6, even 5 inches. I'll give you the benefit of the doubt and say 5 inches. I think our biggest part that we've ever made is maybe like a fist size part, and that was a pain. Like we were struggling to get at it, and tool clearances and everything was so tight. We like to say like maybe like a coin sized part is in the sweet spot of what most people have demands for, and then what we are capable at. But really, the smaller we go, the better everything becomes. Like the cheaper the input material cost, the lower the scrap rate, the more efficient we are. And so we end up making a lot of parts that are sort of, if you think about round bar size, they're like less than 2 millimeters in diameter.
It's about 80 thousandths of an inch for those in the US.
Yeah. Wow. Yeah, something like that. And on the milling side, often we find parts that are like, they fall between the grains of your fingerprints. So that's about like 0.2 to 0.8 millimeters in volume, let's say. And then inspection becomes challenging, handling becomes challenging, measurements of how many parts you made, all that stuff exponentially increases in difficulty. But it provides a nice moat. So as you said, we niche down, and that really becomes our niche when the parts can kind of fit on the tip of your finger. Yeah.
That is cool.
That's wild. I'm sitting here looking at my finger. There's just no way.
Yeah, I'm doing the math in my head, and I'm not great at it, but so a half a millimeter's about 20 thou, 18 thou. Yeah. So that's as before we hit record, Jerry, you guys make chips that are 100 times, 1,000 times bigger than that, I'm sure.
Yeah, exactly. Yeah.
So let's talk a little bit about the actual machining process. So let's start with you, Jerry. So you're taking either, huge billets or big forgings or big, big I-beams, or I don't know what,
Sure.
clamping them somehow and using
really.
what size tools to cut all these things. Maybe just give us one of your last really big parts. What was it for? How did you approach machining it? What was the plan?
Yeah, so we had a couple, actually many assemblies now that are coming to mind that, basically fabricated here. So some of it was comprised of billets, some stuff that we bump formed into a rough shape, and then some were forgings, a stainless steel that we fabricated, welded together, and then we started going into the machining. Surprisingly, we're not using, really big, ginormous cutters. We're talking, anywhere from like 2 to 6 inches diameter is about the tool size that we normally go at. And one of the things to keep in mind is to fabricate some of the stuff or machine it, you want to not impose a lot of heat to your work part. So that'll kind of slow down on distortion and things. So besides not being too overly aggressive when you're cutting, but also using a smaller tool to limit how much heat that you're going to apply to that part to kind of manage that stress and heat to avoid warping and things like that. So yeah, starting out, that's what you're looking at, but 2 to 6 inches.
Now, that's not as big as I was expecting. So a 6-inch face mill you'd be removing material with?
Exactly, yeah.
And I'm sorry, did you say like a lot of these might be weldments that you've put together? and then you're coming back in and hitting.
Mhm.
I know, like, so we do a lot of that where we're welding together several components and then coming back to bring a bowl hole circle and O-ring groove in the tolerance or something like that. Is that a lot of what you're hitting?
Right on. Yeah, so a lot of the stuff that we look at, we'll fabricate heavy and make sure there's machine stock, but yet we don't want to start with like a giant billet or ingot that's 6 feet thick. I mean, there's no reason for that. So obviously sometimes there is, but in some of the parts that we look at, we'll try to fabricate them close. So maybe they're within an inch or two of finished sizes, and then from there we'll finish machine it. So again, we're first trying to be a little bit. There's a method there to think of not over machining and over removing stock for the subtractive service that we're talking about here.
That just makes sense. Yeah, you can get it close and have less.
Yeah, we do almost the opposite thing or something similar where we use additive manufacturing quite a bit. And that's something that Lincoln Electric produces large format, through the wire arc additive manufacturing. So it's a robotic arm for welding, and we'll make products that way as well. We can print parts that are 10,000 pounds and, laying down 10 to 15 pounds an hour of material. And in that regard, we're printing, again, just enough to have machine stock, but yet have your finished part, and you're lessening that risk of stress and overwarping.
Wow.
That makes a ton of sense. So how are you work holding these kind of parts typically?
So that's another thing that's a little challenging too. So since a lot of times you're not starting out with just a square billet, so we will either fabricate or 3D print, or we'll put our own fasteners like feet on the parts. We have our own fixture system that we use here that are like 50 millimeter spans in between each one. And that's basically will hold and locate your part from one machining center to another. So you may start out roughing on one machine and go to a semi or finish or different setup. We'll use those same pickup points. So it's basically like a glorified shoulder bolt, but it has a few more inserts in it. But basically it'll hold your part and locate your part without having clamps or anything over it. So it's more freely open for full machining and access for undercut flangings and 5-axis hole work and stuff like that. And then from there, you'll at the end of it all, you'll end up cutting those off, and those just get discarded or scrapped. If there's some way, so every now and then with parts big enough, we can fashion or design those holding pieces within the part, and then machine it away again at the end. Quite often around the outside.
Wow, I just got my takeaway. Paul, you've been in my shop. You've seen those manifolds we make for the oil and gas industry. And so we make a bunch of components. We weld them together. They go to the mill for final machining. They're usually somewhere between 30 minutes to an hour of machining at the end, that last operation.
Mm-hmm.
And there's usually 30 minutes to an hour of loading and unloading that in the mill and getting everything indicated incorrectly. So we've been, for a couple of years, we've been sitting here trying to figure out a better way to do work holding so we can have quicker change out. And what you just said, I think it might be my takeaway. As soon as you said that, I was picturing like how we could early in the process put just a couple sacrificial.
Salt planet.
Yeah, that's cool. Okay. I got all I need.
It helps quite a bit. That's good. Glad we get help. Yeah, that kind of stuff helps quite a bit.
And Josh, talk us through a little bit of what's typical work holding for your types of parts.
Well, it does vary a little, but there's probably 2 or 3 main workflows that we have. A lot of the time we approach parts from solid, I guess, is the best descriptor. We end up using something like an ER collet, holding round bar, and then trying on the 5-axis mills, especially trying to get 90% of the features in one hit. A lot of the issues come from the bar itself being quite small. So if you start off with a 3 millimeter bar and it's projecting, let's say 30 millimeters from your collet and starts vibrating, all that stuff becomes a problem. So when you back yourself into that corner and have to start from sort of inconvenient stock sizes, often we start utilizing glue or adhesive based work holding. So these parts clamping is like a non-starter. Like you can't hold this thing in a vise if it's a millimeter in size. And glue comes in like really strong there because it's a semi non-influencing clamping strategy. It's not going to bend and twist and warp your part, but it's going to provide a lot of holding force. And so then the issue often becomes that you want to use stronger and stronger glues, and they get harder and harder to deglue. As your surface areas get really small, you want high bond area and like high bond forces. But then you deal with these like super nasty glues that if you do it wrong, you've permanently joined. It's basically like welding. So,
wow.
We ended up, I think last year we ended up buying something like 200 liters of acetone, which for us is actually an insane amount, considering the part size. And that was still dwarfed by the cost of the glues that we ended up using. So all these Loctite products, the fancy ones, they ended up costing an arm and a leg. So that workflow is pretty common. And we also do a lot of wire EDM. So you end up having some workflows where you attack most of the part in the milling machines and leave a significant, let's say, tap, something that's still rigid enough to accept all the machining operations, and then move to the wire EDM and just slice off the part, sort of like a deli slicer. And that's nice as well. It's like low force. I think this is maybe a common theme between all machining. It's like where are the stresses generated, especially if you're looking at really long parts where if you start touching it here, does it move over on the other side? And for really small parts, it's the same thing. It's like if you've started to put a lot of stress into your raw material, if you purchase this drawn material that's from an unreliable supplier, it's like you're never going to make good parts. And similarly, during your process, are you putting stress through a dull cutter? Is your cutter just like 10% too dull and starting to influence the material properties, and you're never going to get a good part like that either. So yeah, maybe that's a little bit of an insight.
Yeah, there's definitely some similarities there, talking about, stress in the material. Jerry, I didn't realize that additive was such a big part of what you guys do. I'm sure that's new in the last many years.
Yeah. And I'd say the last 5-6 years, it's really come on pretty hard. Large format printing, like that. Printing parts that are 8 feet tall. Yeah, that's been really good for us. Especially on the tooling side, and then we're seeing components made of it now. Forgings and castings, take a long time, so we're able to save weeks, if not months, off of timing going to the additive route.
I was just going to say, Jerry, what's the hardest thing about managing some of these 20, 30, 40-foot projects?
The hardest thing, I would say, is most of those are again either fabricated, through additive or traditional fabrications. So materials probably not too bad. I would say just handling. It takes a while. Like if you think about how long something takes to machine, but like to your point, Mike, you were talking earlier. Well, it just takes some time to get it set up in the machine and get it trimmed in and whatnot. So we'll have a lot of our pickups, like something that big. We'll use a laser puck system for pickups. The fabrication guys are using that. They're actually developing it, putting it on, and then that same information is transferred over to our machine shop. So they're picking up the exact same points and coming up with their own strategic pickup for the machining side. But then it still takes a lot of time to maneuver that part and flip it over, roll it over, different setups. I would say that's probably the largest challenge of it all.
Yeah, so you might have, I can picture where, like I gave the example of 30, 45 minutes machine and 30, 45 minutes load, unload. I guess in your case, that could be, that's probably more in several hours, maybe a day, I guess. Yeah.
Several hours. Yeah, absolutely. Yeah, we've had 5-6 hours isn't uncommon for rig a part into a machine. Wow. Absolutely. And you do that. It's not a big deal if the part's going to be on a machine for a week or two. Fine. That's not a big deal. Quite often we'll move something over to a machine and just put some 5-axis holes in it. So the machining aspect might be only 6 to 8 hours, but you spent 50-60% of that just put
I could see that even being difficult.
Just you're going to do the same thing.
I could see that being difficult even during the estimating phase. Just how long. Just figuring out what the touch time is.
No doubt. You got to think of all that machine time. It's not always spindle turning time. you're charging or you're getting cost to that machining center. So yeah.
Jerry, what size cranes capacity wise are you using?
Yeah, we got a bunch of them that are, I mean, all the buildings that we have here have cranes in them. They vary from, 10 ton, 15 ton, up to 30 tons. 30 tons are our biggest one. So we've had some parts that were a little bit heavier than that, and then we would just actually source some riggers to come out and put it on the machine. Quite often, that's usually only needed in the beginning. And then once we machine it, rough it out,
Light
then it
enough.
becomes, okay, something now we can manage with
Wow,
our
yeah.
rough. Exactly.
I've never even
Yeah.
thought about.
Machine a couple thousand pounds come off. Okay, now we can handle it with our cranes internally. Yeah. So, but yeah, 30 ton is our biggest one right now.
I've never thought about hiring riggers to come put the material on the machine until
No.
it's light enough that you can take it back off again.
Yeah, I haven't either.
wow.
And then I'm curious to know, when you need to flip a part over that weighs 20 tons, how do you actually do that? Do you have like special mechanisms on the crane that like rotate?
Yeah, our guys do have a lot of special facility, booms and different things that they use to flip parts over and spin them. Yeah, they do. Yeah, they've quite the outfit over here. These guys are trained. We have a group of people over here. That's all they do is machine setups and rigging parts and moving things around with the cranes. So yeah, they stay pretty busy just doing that.
I know in my shop, we sometimes did parts where, again, more the size of Mike's parts, but where we had, because of material removal and movement of the material, we had to, flip it over a few times, rough it, semi-finish.
Yeah.
Do you have to do that as well, where you're flipping with a crane, these massive parts multiple times?
Yes. Yeah. Yeah, especially if, like I said, you're removing a lot of material and some areas are getting thinner. You're worried about heat. So again, that's a smart way to do it as you go at it. For a lot of times you guys know when you first hit that first pass and you get that outer layer off, and that sometimes relieves a lot of stress. So then you're going to want to flip it over, do the same thing on the backside. Sometimes you'll see that material move again. So yeah, it's very, very common practice to flip things 2 and 3 times. Absolutely.
Josh, I imagine that's not you just starting with billet mostly, and it's 2 or 3 millimeters in diameter, and you just throw it in the machine and you're ready to go.
Yeah, just press the green button and make cash. Yeah.
Your material handling is your fingers.
Yeah. A lot of the time we use sieves, and it's funny. You start to end up buying really random stuff that's non-machining related to help you handle parts. So about must have been 4 or 5 years ago, we were making a lot of these tiny pins on our Swiss lathe, and we're starting from 3 millimeter material, and the biggest OD was 1 millimeter, and the smallest OD was 0.2 millimeters, and the whole part was about 1.5 millimeters in length. So it's very small and just annoying to hold, and it's kind of sharp. And the boys were complaining that you can't really hold these en masse very easily, and you have to picking them one at a time with tweezers from an oil bath or a little container is just not worth the trouble. So went to the local tea shop, specialist tea shop, and I pulled out these tea strainers, and they had every single mesh size you could ever think. You had mesh sizes from 1 millimeter mesh to 0.1 millimeter, and I got one of each of these strainers. And that was Christmas for the guys. They could now pour the whole tub of oil and parts, and it would just strain all the oil away.
Wow.
But since then, you develop other techniques, you make your own little strainers, and you buy mesh and sheet and then laser weld it all together to make these little cups. And that's really all the handling that happens from the machine, because if you start touching the parts too much, you mark them, and a lot of the components we have aesthetic, requirements too, or very, very tight scratch and dint requirements, especially for the medical industry. So you can't generate burrs or non-conformances from just handling. So yeah, then you realize that you're pretty T strainers that are made from stainless steel are no good because they're scratching the parts. And so you have to make plastic strainers, and you end up drilling like thousands of holes to make your own little plastic billet strainer. And then on the other side, when you do have to really start touching the parts for inspection or for like even like microscope visual inspection, we grind a lot of our own tweezers to get, like, you buy commercial tweezers and they're just not good enough. And so you have to end up grinding the tips and facets, and just like making a tool or grinding a tool, so that you're picking up the parts in just the right way and to not scratch them or influence them. But yeah, those are, I guess some of the pain points and then joys once you figure them out.
How hard is it to not to lose parts that small?
Oh, no. That's, you lose them all the time. It's like a constant battle, but you try to make workflows where the part manufacturing is not the biggest burden. So on the Swiss lathe, if you lose a part and it drops on the ground, fine, just make another one. But on the milling machine, you have to have automated workflows so that if you do drop a part, and even if it's a 10 or 15 minute cycle time, your process is stable enough that it's not a huge burden, because it's just a fact that you will lose them, you'll drop them, you'll damage them. And a big issue is that if a part drops on the ground, it's so small that you can't really identify if the part that you've just picked up is the same part. It could be a chip, it could be a part from a previous batch. We try not to have that problem, but as soon as it touches the ground, it's just instantly NG. And having a process that creates good parts to feed into a maybe less capable process down the line alleviates that pain.
So what type of, so like when we're estimating parts, if, we assume we're going to have 1% scrap.
Right.
So for every 100 parts, we're going to make 101, right?
Yep.
In that scenario, I mean, what does that rate look like for you?
It depends a lot on the tolerances and the requirements on the part, but I'd say on average, we're producing 10 to 15% overproduction. For a lot of our internal parts, where for the watch especially, that's like 200 or 300%, because the parts from the machining side, because the parts go through so many downstream processes that each have their 10% failure rate chunk, that you might end up making 200 parts to make 80 nice ones or 50 nice ones.
Wow, so that's through defect and just lost parts and everything. I mean, you could be anywhere from 10 to 30% or more.
Yeah, that's right.
Wow.
Yeah.
That's never happened at Baker Industries, has it, Jerry, where you drop a part and you can't find it?
No, it's obviously you see the same things. If you drop a part, it could be damaged, right?
And it's a lot, and it might damage the building.
Yeah, I was going to say, it registers on the earthquake monitoring equipment.
For sure. But yeah, we don't do too much, in like that high volume type of stuff. So, that we specialize in one-off or low volume numbers. So yeah, we can't afford to have those kinds of that kind of turnaround for sure. There's no way. But luckily for us, most of that stuff is recoverable.
Sure.
As you get to weldment or things that we're creating, a lot of things can be touched up and repaired with weld. So normally it's not an issue.
Okay. So let's talk about inspection and measuring. You alluded to it a little bit, Josh. Let's start with you, Jerry. How do you guys measure your parts?
So, good question. High accuracy and tolerances, flight hardware and stuff, that's going to have to go on our CMM machine. I think it's one of those parts, CMM machines, I think the biggest envelope is right around 8 feet or smaller. So anything bigger than that, most of the times we get a little bit bigger, lower tolerance, and then we'll revert to either a white light scanner or our laser trackers. And that's the lasers we're using for setup as well on it, but during fabrication as well as CNC machining. So those pucks will stay in place or get certified again once it's over an inspection.
Yeah, we had a laser tracker at our shop for some of the bigger parts that were bigger than our CMM. So when you're talking maybe some of the biggest parts, maybe you have bores on two ends of a 40-foot part. What kind of tolerances are you able to hold?
Yeah, a 40-foot span, you're probably I'm going to guess like 10 to 20 thou in that range.
Wow, okay. That's pretty tight. That's about as big as some of Josh's parts.
Yeah, it is. Yeah, it is.
Your
Yeah.
whole part fits in the tolerance of,
Right.
the distance between those holes. Okay, laser track. Okay, and then for smaller things, obviously just bore mics, micrometers, things of that nature.
Yeah. I mean, like we consider anything that's the tight tolerance. It's if it's like between 3 and 5 thou, that's considered like something that's gonna have a special look at it. And then we're able to machine comfortably within a thou, sometimes 8/10. Then anything after that, then we're looking either getting into grinding it, or definitely we're looking at if it's usually it's specific features, and then in that regard we'll look at it with like doing hole moves, or put it in undersized and bring it in either by hand, or go back on a machine after it's been inspected.
So occasionally when I'm doom scrolling machining videos on Instagram, I'll see one where they have like a micrometer that's like 6 feet across. Do you have micrometers that big?
Yeah.
Okay.
No, I don't think so. Not that I've seen. No, definitely not.
And Josh, you mentioned microscopes. Let's just talk about the kind of tolerances and types of equipment you're using.
Yeah, it's interesting because small parts have been made for a very long time. I mean, watches have been around for hundreds of years. So turn of the century, like 1900s, industrial mass production of watches was around. So the inspection methods have been around for a very long time as well to support that, although they've definitely developed. From like a more holistic side, the early watch industry did like a lot of matching. So similar to like the gun industry, where you'd make a part and find the matching part and put it together. And that really changed when they started using hard gauging for a lot of the parts. So you'd make some masters, plug gauges, like basically ring gauges, and you'd start to eliminate matching, or you'd be matching against a master really. And I guess the next biggest phase in that historical development of measurement within the watch industry came when microscopy and profile projection or shadow graphing was economical. So you'd have, your machine and then a shadow graph right next to the machine. You'd be doing constant, make one part, measure it on the shadow graph against a template or like an overlay, and make some adjustments, make the next one, and have this feedback loop right next to your machine. So that's the historical approach. And then in our workshop, we've got this beautiful like Mitsutoi, like state-of-the-art, brand new shadow graph we bought when we first started out. And we used it a lot. Same thing with the overlays at like maybe 100x or 50x zoom. You calibrate your overlays against some masters. You might have a ball or like a ceramic ball or a gauge block to calibrate your overlay, and then you start to measure your part. And about a year ago, we took, I guess, the next step, and we bought this, state-of-the-art Zeiss CMM that's optical and tactile, and goes down to like a 0.2 millimeter tactile probe. So you're able to get into the small bores and tiny features. And there's a 700x zoom lens on it. So you can really like,
wow.
Yeah, it's just nuts. Like you can, we've got a part that's got a 70 micron hole, right? So it's it's two holes that are intersecting, right? Like a T. And you have to measure these two intersecting holes. And luckily it's made from like a clear plastic so you can see through it. And you can blow those holes up. So they're basically the size of your entire monitor on the screen. And you can start to measure them. It's like Lego blocks. Anyway, so we've got all these nice methods, and I've, made this big CapEx investment into this fancy Zeiss machine. And one day I walk into the workshop, and one of the guys, he's scratching his head a bit, and I see him walk upstairs to the inspection area, and he just turns on the profile projector and starts measuring back on the thing that I'd replaced with this fancy piece of Zeiss equipment. He's like, "Yeah, I just think I'd get a better feel for." I'm sitting there like hands in my head now. So inspection is really challenging. Like even with the best equipment, you end up reverting to these core principles. What's your master? Like all measurement is comparative. Unless you're in the NIST laboratory, you're not really doing absolute measurement on anything. And even then, comparison in a workshop is subjective as well. Like, what's the temperature of your workshop? So we keep a plus or minus 0.5 degree temperature tolerance in our workshop. So that's just mainly from the machine side. So the machines don't grow and they don't move, but also on the inspection side. So your inspection equipment isn't moving and growing constantly. And then you start to ask, what's your master? What are you comparing against? On a profile projector, I guess you've got the scales of the table. That's okay. But having a hard master, like a sphere that's got a calibration certificate or a pin gauge that's been measured in a more accurate way, these become your standards in the workshop that you're always tying back to. So, like, even on the Zeiss CMM, like, CMMs are amazing, incredible piece of equipment. But before we measure a very tightly toleranced part, especially with GD&T against three datums and holes and bores that are linked up against each other, we run through our entire calibration procedure against that master sphere just before we start measuring. So you might have 30 minutes of measuring on the machine that, unless you calibrate the machine just before you start measuring, could be just wasted because you didn't calibrate initially. Wow. So when you start chasing these microns, everything matters. And more than, I guess, like anything else, you got, I guess, temperature is the main error, but then cleanliness of the parts. Do you have hairs and dust or oil on the part that's going to affect your measurement? Secondly, do you have burrs? So what good is an optical measurement solution if your bore has burrs that the chamfer has put into the bore, and then all your bores look undersized, and you take a pin gauge, bust through the bores, and suddenly they're oversized again. So all these considerations, I always say I'm never an expert at anything, but I've just made a lot of mistakes. And you quickly learn from these mistakes and try not to make them again. And handling these small parts, it's just, learning from your mistakes.
What's the typical tolerance you're dealing with?
Yeah, it's a good question. We have a split that I think our internal work, something like 80% of our parts have a tolerance of plus or minus 3 microns on them for our watch work. So there is a tolerance on the part that's plus or minus 3 microns. It might not be the whole part, definitely not the whole part, but it might be like a bore, like a 0.5 millimeter bore plus or minus 3 microns. And that might be the diameter, the roundness, and the taper of the bore. So some sort of like quasi-cylindricity tolerance. We're not really measuring that, but that might be the range. And then for our contract manufacturing parts, we have a few parts that have tolerances of plus or minus 1 micron on a feature. And they're very challenging to inspect. And then the most challenging tolerances that I think we have are like a GD&T tolerance against 3 datums of a bore located against like these 3 datums of like maybe 5 or 6 microns. And once you start tying a bore against these datums, your datums have to be super perfect and in the right spot in 3 dimensions, and might be like a bigger tolerance, 6 microns. But as soon as you apply that GD&T aspect to it, it gets real tight. So we that's where we specialize. Like, we often get asked to quote though on parts that have like a plus or minus 10 micron tolerance, but have production quantities. So the first and the last part on a 1,000 part run have to just be in spec. And so plus or minus 10, let's say on the something like the parallelism of 2 walls, two faces, over 1,000 parts, suddenly our manufacturing methods become really viable because of the process consistency. So and then we start talking about CP and CPK and how to optimize your processes to get stable results. And that's where I guess the next part of our journey is really focusing on.
That is mind-blowing.
Can anybody on here, just because I know a micron is tiny, can anybody give a frame of reference?
I have my calculator here.
Okay,
ready.
So a micron is what in inches? Because I'm terrible.
A micron is like 30 millionths.
Wow.
And so when you're talking 3 microns, that's 1/10,000th of an inch, just 11 tenth. But so 0.0001.
Wow.
Now you said the word 17 before. Did you say you made a hole that was 17 microns in diameter?
70 microns.
70. Still, that's less than a 3,000th inch hole. So you have a drill less than 3 thousandths in diameter.
Yep. The smallest hole we've ever drilled is 20 microns in diameter.
20?
20, yeah. So it's like a human hair divided by 5.
That's 8 tenths. There's companies that make drills that are that small.
Yep. I think that, so the smallest drill I've seen that you can kind of like catalog by one-click purchase is 10 microns. And I think they would make you like a smaller drill, but they probably don't want to advertise it.
Jerry needs a caseload of
those. That's crazy, man.
You're blowing Jerry's mind here.
Yeah, I don't know if I'd see them.
I can tell you my eyesight's so bad, I definitely would not see them. There's no... That's insane. I mean, because we deal with stuff.
Yeah.
I don't know. There's probably always a job in the shop that we've got half a thou or something, whatever to deal with. And, I just know like how much goes into that. Right. And now we just split that in by 10. That is crazy.
Yeah. It's crazy.
I think it is actually probably super analogous with what you do, Jerry, in the sense that your operators become so key. And you can have all of this lovely kit and you can have these brilliant machines and brilliant inspection methods. But unless you have the people that are interested in being almost resilient against all the hardship of making challenging parts and dealing with the screw ups and the challenges, like it's just for nothing. So the people are so key. And that's probably the one link that's like universal between the big stuff and the small stuff and the stuff in between.
Yeah, it sounds like it's all relative. Like even you're talking about part warping and bringing holes and things into tolerance. Certain things you're going to have that slower approach, and you're going to be a little bit careful going into it to make sure you hit those. And then people, it's small to extra large. Yeah, it's all relative. The same problems exist, just at different scales, but they're still there, and you have to address them from the very beginning.
Mm-hmm. Yeah, Josh, as you were talking about how key the people are, right? And one of my things, is this thank a machinist hashtag and just how important machinists are to everything in the world. And, I say it's one of the hardest businesses or the hardest business in the world because, you can quote a job, and if you're accurate with your quote, you might quote, I don't know, a 20% margin or something, but you're going to hit that margin if everything goes right. You hit your setup time, you don't have crazy scrap rate. You both have just talked about, a myriad ways that parts can go completely sideways and you scrap a ton of things, or you just take, an order of magnitude more time to dial in a tolerance than you anticipated that it might take. And, on both ends of the scale, it's still incredibly difficult and, takes really specialized skills to get it right.
You've put it very well, Paul.
It does.
Well, thank you to all your machinists for doing their jobs.
Oh, for sure.
What's up, guys? It's Nick from MakingChips. My good friend, my co-host, my partner, Mike Payne. I'm going to give you 3 reasons why you should check out By the Numbers, the new podcast hosted by him. First, Mike is full of wisdom and experience for what it takes to buy, sell, and lead a business. If you look at his entire history, he's done it over and over and over again with lots of success. So he knows all about how to dive into the numbers that will improve your performance. Second, Mike's the first person I call. I call Mike when I have a new opportunity to acquire a business, explore a new partnership, or when I just have data I need to dig through and really understand what's going to impact the performance of my business. And third, you got to love the Tulsa King, the buttery voice that just soothes your soul and gives you the confidence to take that next step in your leadership. Look, if you love making chips, you're going to love By the Numbers. If you want to improve the financial performance of your business, and who doesn't, you should check out By the Numbers by Mike Payne under the Making Chips Network.
As we look to wrap up here, maybe a question is, what is maybe a recent part or project that you were particularly proud of that was just super cool, and the team was just jazzed that you got to do it?
I was just thinking, just some of the stuff that we do, I can't go into a lot of details because some of the government stuff we do, but some of the space exploration components, or you're making parts for, whether it's tools or actually flight hardware for rockets and things. When you start seeing components like that from rocket engine components to structural components for ships or submarines. When just that kind of, but besides the automotive and some of the everyday stuff that we do, like some, structural things for like nuclear plants or energy plants we talk about, it's cool, it's great, but a lot of times you don't even know where it goes or what it's used for. So, how can you put it into, retrospect? But when you're looking at, space components or rockets and the aerospace industry in general, or shipboard components, a lot of those you'll recognize and you'll see those, and that gives everybody a little bit of sense of pride to what they're doing, and especially pull it off, have it really great, especially with the customer side, and that you met their timing and their quality was exceptional. Oh, that definitely makes you feel like it was all worth it for sure.
Super cool. What about you, Josh?
I can rapid fire a couple of projects. So we do a lot of quantum computing hardware. So these cryogenic like manifolds and bits and bobs and brackets. It's all just advanced bracketry, but very precise bracketry. And Microsoft recently announced they had this like new quantum computing breakthrough called Marana 1. And in the video that they probably spent like fair chunk of cash on developing, they pan across their laboratory and there's this lady holding this like little, it looks gold, but it's actually made from copper, this like copper block. And we'd made that, or at least prototyped some parts that go onto that. And that was like very, very satisfying because they'd made us sign all these NDAs and, we thought we'd never be able to see this thing in the light of day. And there they are holding it. And so I shared that video with a bunch of people and said, oh, we made that. And then more recently, we did a project. It was kind of like a university and the government and a industry partner got together and they made this LiDAR sensor. It's a laser distance and velocity sensor that's going onto a lunar lander. And we made the optical housing for it. It's made from titanium. And one of the requirements, so there's this print, right, with all the geometric tolerances. And one of the requirements that was like off the print in the notes was make it look pretty. And so then like we spent hours and hours tuning our tool parts in to make this thing look just amazing. And they started showing it off recently as well. So very happy about that. And the one thing that really gives us pride, this like third project, I guess, is all the medical device work we do. So we work for a company here locally called Cochlear, and they make like an ear implant. So it's like a neural stimulation device. It's implanted, and making parts for that product is just so satisfying because you see people daily wearing that thing. Like you bump into them in real life, and knowing that you're able to help them in a very tangible way feels great. It's like just this crowning achievement. Yeah.
I have a question for both of you. So when each of you were talking about work holding and tooling and some of the things you deal with, I noticed the other one shaking their head like there's no way. So based on what you've heard now in this podcast, who has the harder job?
Jerry, I could never imagine.
Josh,
no. Definitely not.
Yeah, right there, yeah. Josh.
When you started talking about getting riggers in to move the part onto the machine, that's just like. And Jerry, I've got a question for you. Like, how do you handle scrapping a part that size? If hopefully you never do, right? But
yeah, ultimately, we're not. Something that big, it's too big to fail. We're making it right. We might have a lot of time into fixing it and repairing it if something goes wrong. But yeah, at the end of the day, there may be extra heat treat cycles or things like that, and welding and remachining. But yeah, you're right. When something gets to that large and there's hundreds, thousands of hours involved already, yeah, you're not.
Have a lot of rework costs, but not scrap.
No doubt.
Yeah.
Exactly. Right on. Yep.
Wow.
For sure. Thinking about the sizes that Josh is talking about and the microns, and I remember using a shadow graph at times, and I'm like, I couldn't imagine splitting those hairs in half. I just like, that's tough. That's got to be a tough thing to manage.
It was interesting seeing each of you respond to the other person's work with it's on such opposite ends of the scale. You both were like, "There's no way."
Yeah, watching their facial expressions has been.
And
fun.
I'm in the middle going, "There's no way" to both of you.
doubt.
Well, Josh, I'm sure you didn't mention it, but the watches that you guys make are such works of art. They're absolutely stunningly beautiful. I definitely recommend everyone go look up Nicholas Hacko watches. They're beautiful. So I'm sure those
I'm
are
going to do
Thank
that.
you.
also
for sure.
very proud.
That's very
proud.
kind, Paul. Thanks.
Yeah,
Jerry, I would buy something from you, but I don't have anywhere to store it.
I hear you. Yeah. You need a garage at least, right? Yeah, no doubt.
Well, gentlemen, thank you so much for joining us. This has definitely been a fun conversation. It hit all the buttons for what I was hoping for when I envisioned this conversation, and I can see the mutual respect on both sides for what the other person does, because it is
Sure.
challenging in its own right and amazing in what you guys do.
Absolutely. Yeah, it is. Yeah, thank you also.
Yeah.
Yes, thank you,
Appreciate it.
Paul.
So, Mike, how do we wrap this one up and get it into our tagline? I'm racking my brain here.
Well, there's something about the size of Jerry's chips versus the size of Josh's parts. I'm not sure exactly what it is, but I do know if you're not making chips,
you're not making money.
bam.
Bam.